talked about that already, but what composes a robot? So the following abstractions could be outlined here. First is the sensory part. We've been talking a lot about the vision, so the cameras. They are the most important sensors of the robot. They give the most information. They are very dense in the sense that they are the density of the pixels per millimeter of the surrounding world is pretty high. There are also others, pressure sensors, inertia measurement units, and encoders for proprioception, for understanding the position of the limbs in the world. The second part, and here we're talking about it from the coding perspective, from the perspective of the software. So materials are not involved today. Then we have to have some kind of a world model in order to interpret the things we have detected in terms of the world geometry. Because we are not in a computer game, we have in the world real normal geometry with distances and so on. So we have to reformulate the phenomena that we have observed in terms of their geometrical properties. The following part is the localization or the state estimation in a more general sense. It is the process of solving an inverse problem of finding where should I be in the state space so that I can observe all the phenomena the way I do. This is done with Kalman filters and other stuff like that. So filters that are based on the stochastic nature of the measurements. We assume the sensors to be noisy and to try to estimate our position as good as we can. The next part is the planning. So after we have understood where we are, after we know the geometrical positions of everything, we can start planning ahead. We can do that. And the last part, finally, is symmetric to the sensors in a way, because sensors are measuring the world and motion is acting in the world. And now we're going to talk about motion. So it is equally important to the sensors, I would say, but it's in a way more difficult. Why is that? Well, because in the motion module, robots become interactive. They act upon the surrounding world, and that causes the feedback loop of interaction with the world. So motion is the key part that actually separates a robot from a regular computer. Regular normal computers, they don't have actuation if we do not count the fans for cooling, but that's not the same. And robot is actually a computer with motion, if we're talking very informally, very briefly. This is the difference. So cell phone is not a computer, and automatic vacuum cleaner is a computer indeed. So why should we talk about motion? Not only because we're doing humanoid football, but also because walking locomotion allows for something like you can see in the left image over here. So the car is stuck, and the human has no problem of going around. So walking mechanisms are very good in terms of their versatility and they're adaptive to the terrain. And yes, here is the slow motion of the kick. There are multiple different kicks. This is the strongest kick. So indeed pretty strong, but you can use it if you need it very much. So these robots could seem like fun and games, but being built in slow-mo, they're actually pretty strong. And they do the skip with their feet again. So locomotion or the usage of the legs is not limited by only moving the center of mass of the system around. There is also something else. We will be primarily talking about moving the center of mass here and there, which is basically called walking. But we have to remember that there are also different things you can do with your legs. So you can interact with objects, like for example. And here are a couple of examples of just different bipedal mechanisms. There's human, and there is also a kangaroo. They do not use the same mode of locomotion as we do. Still, they're bipedal, and they can walk just very slowly. So they have pretty similar mechanical construction as the ostriches, but very different control, so to say. For humans, it takes nearly a year or a year and a half to start walking robustly, or 2 years. And in terms of the artificial mechanisms, it is a still ongoing process. So more than 100 years ago, a pan-tracking platform was introduced, the first walking mechanism. It was pretty simple. It allowed only for linear forward motion. And since then, engineers and scientists try their best. And what we have now are the Unit-3 robots or Boston Dynamic robots. They're good, that's for sure. But they are not on the human level of agility. So for us as control engineers, bipedal walking is very difficult. We have talked about the degrees of freedom of the robot, just briefly. So let's cover them just once again. And imagine that you have a robotic vacuum cleaner. How many servo motors do you need to move it around?
Can you repeat that?
Hmm?
I didn't see it. Can you just repeat what you said?
How many servo motors do you need to move a robotic vacuum cleaner around? What? You sure about that?
4 minutes. There's 6 each leg, right? 6 each leg.
How many wheels are in the robotic vacuum cleaner? Imagine 4. Why? So that's really neat or not? Two. Yes, indeed. So there are 2 wheels in the robotic vacuum cleaner, and it's enough for it as a differential drive to rotate and to move linearly. And here, if we consider everything that is from here and below, there are 12 servo motors, and these are the ones that are pretty much necessary because we have to have the legs to be pretty flexible. We have to reach to very different destinations. So if we're talking about the outcome that we want from our legs, those are the following. You actually have to be capable of solving the inverse kinematics problem. We want to first be able to walk. And the second, while standing, so while the feet are fixed to the surface, we have to be able to move the center of mass, like I do now. I do not move my feet on the ground, but still there is a certain bounding box, or I should say support polygon. So if we project my center of mass on the surface, there will be a certain polygon in which the center of mass could be, so that I'm not falling. And all the servomotors that I have, they allow for these motions, and I can move my body as a rigid body with 6 degrees of freedom. I can move it, well, of course in certain ranges, but any way I need. You can check that. So you can recall the degrees of freedom of a rigid body, and you can check that you can do all of that with your feet. So we really need all of these degrees of freedom for the humanoid robots to be adaptive and usable in different scenarios. And the 12 is not just 6 times more than 2. That's even more difficult. There are constraints from the control perspective, there are engineering problems, and there are stability problems. So here you can see that all these motors are being stacked on top of each other, and if one of them fails, well, then everything fails. All the backlashes and imprecisions, they are all amplified by the length of the leg and the fact that they work one after another. And if a robotic vacuum cleaner has suddenly stopped, well, it's suddenly stopped, that's it. And if a humanoid robot stops, it will fall over and maybe it will be broken or something. So these machines are really much more difficult than a regular, so to say, wheeled robots. So let's take a look at the real physical robots. We have talked about that already just a bit, but let's reiterate. So there are 2 versions of this guy. The left one is the stereoscopic, this is monocular, and they're almost identical, so we can take a look at any of them. Here just there are 2 cameras, and some of the servos are a bit hardware, but the rest is the same. So can you see in this picture where the joints are? Where are the degrees of freedom that we're talking about? Is it clear?
Yeah.
So here 3, here 1, here 2. And the same for the second leg. You will have to touch the robot physically in order to get sense of what's going on there. And we're using the convention from aerospace engineering, yaw, pitch, roll. No, yes, pitch, roll, yaw. We're using the same notation. I mean about the end. And yeah, the head is pretty useless in terms of walking, and arms are used only for the stand-up. So they could be possibly used for balancing. Well, yes, they are used for balancing, but only after the kick. So they're not involved in the main locomotion part, so to say. And they just kept rigid, as if the whole body is weirdly shaped, rigid body that is not moving anywhere. Let's now consider a couple of natural examples of walking mechanisms. There's a bird, there's a human, there's a cat. So a fascinating thing about legs, about our type of legs, is that they're so good that they're used in with very different flavors. I usually ask this rhetoric question about the bird's knees being backward. So, do the birds have their knees backward, or they don't? It turns out that if the bird is alive and well, the knees are hidden under the fur. So we usually see only the lower part of the leg, and those are the heels, not the knees in the birds.
Same thing with the penguin.
So they have the exact same mechanical structure as me, but just very different proportions. And all the birds, they all the time walk like this. They walk on their toes. And why is that? Well, birds are very good at running, jumping, that kind of agile skills. And let me try to jump on the same feet as the robot has. So with no fingers, our robots cannot stand like this, right? So if they could jump only like, it's very bad. It hurts the knees, there's awful noise. But if I only just do it like the birds do, it changes instantly. So what's the thing? The thing is the compliance mechanism over here, the Achilles tendon, the suspension. And birds, well, they don't really know about that, they just use it. But you can notice that people, they run in the same manner. So they use the springiness of their leg, and that will, very far from now, it will bring us some intuition about about what? About running gait generation. But what I wanted to say is that you can see the same kinematic structure through all these three mechanisms. So this part is the same as this part, and actually it's the same to this part, but it's just here in this picture it is not in that state, it's in the different state. However, if this human will try to run, then the structure will be pretty similar, so S-like. And it will be spring, it will be more effective, it will not hurt the knees as much. So we have to take care about the heating impacts as well, while designing the legs. And our robots, the football robots, they are not capable of running, unfortunately. Like the fish are not supposed to talk. In the same manner, these robots are not supposed to run, just because of the construction. So some of the following versions, later versions, maybe they will, but for now it's not possible because they lack some degrees of freedom, unfortunately. But that's fine, because we're not exactly working on the running, we're working on the football, and all the algorithms and team play and utilization and all that stuff, it does not depend on the locomotion mode actually. So, how would we start working on the walking algorithms? What do we need to do to make a step? It sounds sophisticated, but what do we need to do to make a step? To lift a leg. And there's a trick. If I lift a leg, it's very, very natural, it's fine. I can just do it. You can do it as well. But if the robot will lift its leg, it will just fall over like this. So there's something else involved. We have to keep the center of mass, the projection of the center of mass in the so-called support polygon of the contact points. So what is that? You know what a convex hull is? Convex hull of a set of points is the following thing. imagine a set of points. A convex hull of this set of points is the set of points that could be represented with linear combinations of these points. Well, actually, it could be understood much more intuitively. It's everything that is inside of the boundary, so to say. So this is the convex hull of the set of points that I've drawn. Why convex? Because this set of points is not concave, right? So it's convex. And imagine if we have 2 feet on the ground, one, and another, the support polygon will be like this. And if the center of mass at all times is over the first leg, in between, or the second leg, that's fine, the robot will stand still. And when I'm lifting one of the feet, I change the support polygon. So now the support polygon becomes like this, and in order for me to still stand, I have to first move my center of mass to this support polygon, new support polygon. And this leads to the first family of walking gates, the first type of them, which is the kinematic gate or safe gate or the robotic walk. There is even a dance style of moving like a robot. And it has to resemble the slow and unnatural movements of the robots from the 90s and 20s to 2000s. How does this walking look like? Well, it turns out that it looks like this, but just propagated in time. So let me draw that. First we stand on 2 feet, then we move the center of mass to one of the legs, then we lift the other one, then we move the leg, bless you. Then we move the leg while still standing on the left one. And then, the important thing, the support polygon becomes this one. So this is the left leg, this is the right leg, and the support polygon is now like this. Why is that? Because I can move the center of mass from one leg to another statically, pseudo-statically. So the support polygon is like this, and we move the center of mass here, and then repeat the procedure. And actually, it will give you the safe and slow and not very effective gait. If you're not allowed to use your dynamics, you have to move very slowly. So all these phases are there. We move the center of mass to the new desired support polygon, and then we repeat this whole process. At no point in time I have any considerable velocity. So if you will ask me to stop, I can do it at any point. And if I'm walking normally, at first I have to bring my velocity to 0. And while I'm walking normally, I'm not statically stable. So I have to first bring myself to the static position. And if you will ask someone, a child maybe, to walk in such a way that you can clap, and then this person instantly freezes, they will naturally come to this gait, something like this, crawling very slow. You can try that with your younger siblings. They will do something like this because, well, actually because they keep their center of mass in the support polygon. It will be not obvious for them, but it's like this. And if we want to be more effective, we have to include the dynamics into the motion somehow. If I'm walking at the same spot, for example, you can see that there is oscillatory motion to right and left, And I'm using that on the pretty much natural frequency of my body. I'm using that to move the center of mass right and left. So the center of mass is more or less over the support foot, and the stance foot is unloaded. So you can consider the walking as two inverted pendulums between which we are switching all the time. This is the first inverted pendulum. Well, it's unstable. I cannot be in this mode for too long, but you get the point. And we're switching between two inverted pendulums, each of which is falling inward. This is the walking, basically, way below. So we're using various kinds of abstractions. Here you can see the almighty and legendary Asimo robot. It has a lot of degrees of freedom as well. So 1, 2, 3, 4, 5, 6. I believe in each of the legs it's the same as in our robots. And it is difficult to control systems of such dimensionality. So we have to simplify them somehow. We maybe do not care that much about the exact inertia of the left wrist, so we have to get rid of the unnecessary details. And while walking, I myself do not really control and think about each of the muscles that are involved in, the stabilizer muscles. They just walk automatically somehow. So there is a level of abstraction into which I do not have access to. I more or less perceive myself as maybe a pendulum, maybe a holonomic platform, something like this. So we have to introduce a couple of abstractions. And the meaningful enough abstraction is really the inverted pendulum. So if we're going to consider a single stance phase between the switching of the legs, it's really the inverted pendulum in 3 dimensions. And I have to go through a certain trajectory that looks suspiciously like a sine. It's not exactly, but something like this. So I have to, just after the stepping of the leg, I have to go through a certain trajectory, and then the same will be repeated, but just in the mirrored mode. So if I'm walking straight, I have to go along a desired trajectory. That's it, as an inverted pendulum. And the rest, the exact stiffnesses, the exact forces, they will be added on top of this model. Sleep here is not too sleep. It's not like an action, but it's spring-loaded inverted pendulum. It's this thing. It's a huge simplification of a robot. So here you can see a physical robot that consists of a lot of joints, and the mass is somehow distributed over it. And we just pretend that we don't see anything. We're not interested in the tiny details, and we consider the very simple model of a point mass on a single leg that is massless and springy. So we use this model, and what this gives us is the ideal version of what could happen if this point mass will walk or jump on a springy feet. And if we, in the simulation, in the model, instantly switch the feet to the next one, we will basically get a kind of trajectory that the system naturally follows. And then comes the tricky part. So if we generate some kind of this motion on the springy legs, we can reproduce all the states, all the angles, all the positions with the position controlled motors. So we get the ideal trajectory for the ideal model, and we try to reproduce the same behavior, but with the real servo motors. And we are trying to force the system to follow this trajectory. Of course, the model is not precise, and there are noises and everything, delays, but it is indeed possible, and this is one of the common ways to make robots walk. So we use some kind of simplified model, generate the trajectory, and then try to to follow this plan. This is what is commonly going on in the humanoids quadrupeds. There are several control layers actually.
What's the moment point?
Zero moment point is the generalization of the projection of the center of mass. Zero moment point is the point on the surface where, in relation to which your angular acceleration is conserved. So let's suppose you're accelerating somewhere, and if the angular acceleration is exactly zero, the zero moment point is the same as the projection of the center of mass. And if someone pushes me, for example, I have a certain acceleration. So zero moment point is the point in relation to which my angular acceleration will not change. So the jog, the third derivative, will be zero momentarily. It's another abstraction that is used for the planning, so probably we don't really need to dive deep into it right now. It's an important concept, and it's used for the planning, for the local planning of the motion. If we want to control the robot locally, a nice way to do that is to control the acceleration of the center of mass. If we can do that, we're pretty much happy because we can accelerate the center of mass in all the directions. That's good enough. So zero moment point is an instrument to formalize some of the intuitions about that. And now let's talk about going to the canteen. How would you describe precisely what do you have to do in order to go to the canteen? Generally speaking, you have to perform some kind of erase that. You have to perform some kind of planning. So you have to go to the elevator, then go downstairs, then move around, and then you're happy. You can have a lunch. But if we have such a general plan, it does not tell us where exactly to place your feet, how to open the door, what to do along the way. So I'm basically talking about different levels of abstraction. You can see them as the maps with different scales. So if you're going very, very far away, you will probably need a very general map where you can trace all the path, and the maps with higher scale, just scaled up maps, in order to move around the streets. And here's the same, but it comes in the state space, but the intuition is similar. So after we have planned the path to the canteen, in which form would we write down this path? Well, one of the ways of doing that is, we can say, approach the door, open the door, approach the elevator, then do something like this. So we can use only the coordinates. We disregard the velocities, we disregard the orientation, and on this level, our state is just two numbers, x and y. If you're telling someone how to go to another building, for example, you don't specify that they have to be rotated counterclockwise all the way. You don't usually do that because it doesn't make sense. It's enough for us to have a very small state space of x and y. That's fine here. And if we have this rough plan, we can we can supplement it with the details about the movement of the center of mass. So if I have to approach the door, I actually have to swing my center of mass to the right and left as I'm walking. So we can plan this, we have to plan this ahead, and I don't want to step over anyone's legs, so I have to perform the foot placement. And as a reference to this process comes the very general trajectory and approximation. And on top of this approximation, I'm planning the exact motion of the center of mass and the foot placement. The model here is more complex. The model is usually the center of mass with the dynamics. So x, y, z, x dot, y dot, z dot, meaning the time derivatives. Probably no orientation, but it depends. I'm talking about the common cases. So the state vector here should include more coordinates, z coordinate included, the velocities, maybe the angles, and also we have to keep an eye on the foot placement, but legs are considered as massless rods that instantly change the place where they are, where they support the body. So this is still an abstraction, but it's just closer to reality, to the real dynamics of the reality. And the next is the so-called whole body planning. It speaks for itself. We have to understand the exact motions we have to perform in order to follow the plan from the previous level. So we know the foot placement, we know the desired motion of the center of mass, then we have to place the foot finally to start going. So this is the level that is called whole body planning. It is often skipped in simpler robots because it's computationally demanding. But, well, not like exactly skipped, but it's being solved suboptimally usually, a lot of the times. But the thing that happens here is very important. Actually, this level of control is one of the most difficult, one of the most challenging. It's the most recent papers, a lot of the most recent papers are exactly about this. Because we have to plan the dynamics of a very complex system, very high dimensional, and we have to do it in real time. We have some reference signal, but we also have, from the other side, there are noises and delays and unpredictability of the surrounding. So this whole body planning is really difficult to perform. And it's done with the techniques that we are going to start covering tomorrow and the day after tomorrow. This is MPC model predictive control. This is the thing that uses the model of the system to predict the behavior and to optimize the control to a certain horizon. Usually not very long, but it could be enough to have the horizon of a couple of seconds in order to plan for the exact motion of all the limbs, all the muscles. And here on the right you can see that the frequencies increase. Why that? Because on each next level of control, we are more immersed into the exact details of the surrounding. So if we are on the first level, someone can tell us, well, the canteen is not working. Okay, let's go somewhere else. You can decide that in a time of like 5 seconds, 10 seconds, that's fine, or 1 second. So if the orders are like this, it is not very reactive. Since the horizon of the planning is quite big, 10 minutes, 5 minutes, it is okay to refresh this plan every now and then. No, not like 1,000 times a second, and it's okay. Regarding the foot placement and center of mass, we have to do it faster. Because if, say, I don't want to step over this cable, I have to replan my motion pretty swiftly. So usually 10 hertz is enough. These are the rough numbers. You can see here that I'm not talking about any exact and specific robot. Those are the generalizations just to make sense of the different parts of the control. What are they for? How do they work? How complex they are in terms of the model and computations? Yep. And the next is even faster. So this will allow me to adjust my hand. For example, if I'm lifting something heavy, I will have to adjust my grip. And this comes, for us, this happens very naturally and very rapidly. For robots it does not, of course. Nothing comes naturally with them. And we can count on the orders of 100 Hertz. So 50 is fine for some applications, 500 is fine for other applications. The next, even more local level, is the individual servo motors. And a single servo motor is a system that is trying to move its shaft to a desired position. So now the model is very detailed, all the servo motors, but each of them are separated, they're decoupled. They are just individually sitting in their limbs and trying to perform the actions that were commanded by the previous level of control. That's why they can work on crazy high frequencies. This is sound actually. This is we can hear these frequencies, and they perform the update of the control loop on such frequencies. And there is another way of kind of control, which is the hardware. So there is no actual control, no control signal, but there is the design. And it's better to solve the problem with no control if you can do it. It's better to solve the problem with passive control, reactive control, not the active control. An example of that is, well, let's consider the car that is supposed to move fast enough. And we have two options. The first option is the fan that is blowing upward and exerted the force on the car so that it sticks to the road. This is the first option. And the second option is to make it spoiler. I mean the anti-wing on the back of the car. Clearly the second version is better. It is reactive to the velocity, so it works just automatically, just naturally. The force is produced as an instant effect of the motion. So if we are not moving, there is no force produced. If we are moving, there is force produced. There are no moving parts. There is no need in electricity or anything like this. So if you can do something without complicated control or even a control system at all, it's better to do it this way. The lever that is closing the door, this is a good mechanism. The architects, they could probably install a servo motor here, but it's not needed. We open the door, some energy is conserved, and after that, this energy is used to close the door. This is genius. This is good. And servo motors are really not necessary there. So in all these robots, we cannot expect a passive robot with no servo motors to walk. This is not happening. So that's why we are concerned with installing servo motors and controlling stuff, because the things we need these robots to do, they do not happen themselves. That's conceptually what is going on. And with all our control, we are trying to bring the state of the surrounding world to a certain desired one. That's what we're trying to do. One of the options here is to just move the center of mass. Well, what is locomotion basically? It's moving the center of mass from one position to another position. So we're trying to change the state of the world so that the center of mass has moved. And why did I write infinity here? It's the sign of infinity from LaTeX. You know that? No? Yes, LaTeX. The marking, what's it called? Marking language. So here we have sensors and planning, Dijkstra's algorithm or other graph searches. Here we have, well, again, sensors, planning, computation. Sensors, planning, computation, the same sensors everywhere, but just different abstractions. Sensors, planning, computation. And here we have no sensors, no planning, and no computation. This thing works with properties of the material. And the control here is performed with the speed of sound in the material. So it's very different. However, it could be conceptually introduced into the same framework.
So if the robot is built something like this, it will not really fly that good. That's what I'm talking about when I'm talking about the hardware. So there are limitations and more difficult and more easy problems for a certain build of the robot. Same for the humans. That there are people that are capable of playing basketball very good or lifting weights very good, and they're usually built different. They have different frame, different muscle distribution. The same goes on here. So we always have to understand our platform. These robots, these football robots, they will not be capable of running just because of their build. And quadricopters, for example, will be, well, small quadricopters will be not capable of lifting 10 kilograms. That's not possible. So just keep that in mind. It's obvious, but still. Go ahead. On the left, you can see the servo motor, the gearbox. On the servo motor, the Mixel MX106. And here's the rotor, here's the gearbox, and this is the output shaft. So a part of this thing sticks around, sticks from the body of the servo motor, and the flange, the detail is fixed to that. The thing about those servo motors is that they produce a lot of torque with not really very fast movement. So they can, the maximum rotational velocity is 55 rotations per minute. So nearly 1 per second. That's not a lot, right? If you compare that to some motors from the, I don't know, USB fans or something like this, or fans from the computer, they go very fast, 2000 rotations per minute. And the output shaft here is rotating very slowly, but the gearbox is nearly 200 to 1. So the rotor itself rotates very fastly, and after the gearbox, the angular velocity is significantly reduced, and the torque that the motor can produce is, on the contrary, increased very much. So these motors are pretty precise. They can produce a lot of torque, but they're slow. And I was jumping with awful sounds on purpose. If the robot is jumping with this type of servo motors, they cannot really react and roll back so that they don't get this hitting impact. So let's take a look once again. Here I'm jumping normally, and my feet are reacting to the moment of contact with fast enough motion. It's soft, but it's really fast enough. And the problem with these servo motors is that they cannot do that. They're not reactive that much. And if at the moment of contact a high torque is being applied to this gear, this torque is propagated through the whole gearbox up to the rotor, and the rotor has to start moving very rapidly, and that's not possible. There is a problem with such gear ratios. The gear ratio here is approximately, I believe, well, it's something like 225 or 220, and the energy that is conserved in the rotor here is the following. Well, if you just rotate the rotor itself, the energy will be the moment of inertia times the angular velocity squared over 2, if you just rotate the motor normally. And if you rotate the rotor through a gearbox, it will be different. The angular velocity here is k times smaller than here. and the other way around. So if we rotate this gear with an angular velocity of omega, the angular velocity here is k omega. So the energy needed to move, or not to move, to accelerate this gear to a certain angular speed is quadratically dependent on the gear ratio. That's very bad. Here's 225, so it will be around 5,000 times the energy needed to accelerate the rotor polar. And the motor actually has to do it itself. So we're applying torque here, and we want this gear to rotate with a certain speed. Actually, we have to start rotating the rotor in the same direction for the whole servo motor not to try to stop the leg. It has to bounce slowly, not be rigid. And because of this gear ratio, it is not possible. And during the heating impacts, these servo motors, they're pretty much rigid, so they just get the heat, and that's it. That's why they're rigid. And it could not really be fixed with the programming. It's the part of the mechanical construction. It's the property of these servo motors. They have a maximal angular acceleration of, I believe, 2,000, approximately 2,000 degrees per second square. So that's a limited value, and it's not infinitely high. That's why these robots are not running and not jumping. Once we have tried in Korea during the competitions to participate in the triple jump with these robots, and we just broke 2 knees during one evening, and that was it. So since then we have not tried. Yeah.
So these motors, they're located in the joints.
Yes, exactly.
For the feet, for example, it's in the ankle part.
2 in the ankle, 1 in the knee, and three over here. 1, 2, 3. The good news are that there is an alternative. So instead of using very high RPM, rotations per minute, high RPM rotor and a big gearbox, we can use relatively low RPM rotor like this, and just a small gearbox, maybe 10 to 1. That's much better because it will give an amplification of just 100 compared to several thousand. Oh no, it's not. I have miscalculated. It's not 4,000. It's 40,000 actually here. So it's very bad, right? You will have to move around the limbs of the robot. You will understand the internal inertia of this rotor. It will be really evident. So if you just slowly move the limbs of the robot, you will feel that it is kind of acting against the change of the angular velocity because of this very high inertia that is hidden inside of the servo motor. And what can we do to mitigate that? We can use this type of motors that actually came from the quadrupolters. So it says something, right? If motors from the quadrupolters are used in robots, these robots are explosive very fast. They can accelerate very rapidly. And exactly this type of motors is used in the robotic dogs and the best of the best, the state-of-the-art dynamic humanoids in the majority of them. And the trick here is that, well, you're probably used to motors like this. There's a cylinder, there's a shaft, in the middle, well, there are options. They could be brushed and brushless, but anyway, there is something that is rotating in the middle, right? The rotor. I'm not a painter. that much, but this shaft is rotating, right? And it produces the torque because of the permanent or electric magnets over here. This is the normal motor, and this motor is just different. So the rotor here is on the outside, and the stator is inside. This part is fixed to the detail, to the body. And the external part, this thin cylinder, this thin circle with the magnets here, the permanent magnets, it is the rotor. And these motors are called outrunners because they have external rotor. And the thing is that you can check, you can see the sheer amount of torque that this would produce, right? So this is a thin cylinder, and it will give you a high RPM but low torque. And here on the contrary, so imagine what torque will be produced if a force is produced tangentially over here. There's a big lever. And this is the great difference between the old-fashioned construction of the rotors and this. Those motors are, well, not flat, but they're very thin in the Z direction. And they have a very big lever. Well, it's not drawn to the scale, of course, as well as this one. But this exact motor is, well, something like this. So they do not have high RPM. They have crazy high torque. And it is enough for these motors to have a gearbox of 1 to 6, 1 to 9, 1 to 10, something like this. And they become backdrivable, which is awesome. So imagine something goes wrong. Robots fall over, and robot falls over, and what do you need to do? Well, one of the best things to do is just to switch the power off and wait until everything stabilizes. And if you just stop, if you just halt the electricity, the robot will continue to fall, and a number of external forces and torques will be exerted onto the limbs. And if this this servo motor is backdrivable, if it's soft, the situation will settle. So if the robot is hitting the wall, for example, with its hand, well, okay, if the robot is soft, if the motor could be driven back with no power, it will be better than a very rigid motor that is not backdrivable, and that will resist to this impact with all of its gearbox. So these motors are really, they seem to be the future of dynamic robotics, and they're used in all the robotic dogs you can see. They are, all of them pretty much follow the same PhD thesis from 2016 of a single guy. That was a good PhD thesis. There's another way of approaching the heating impacts. If we don't want to hurt our servo motors while landing, we can introduce so-called serial elastic elements. What is that? Imagine that, well, it's basically like a rotary spring. So I don't want to hit the wall, I can carry a spring before me, and I will first bounce. And this is the same work but for the rotary motion. So what is done here is that after the output shaft, a rotary spring is introduced, and all the heating first goes through this spring, and if this impact is very rapid and very powerful, it will just go through the spring without imposing a considerable torque on the motor. Seems reasonable, right? And it's a low-pass filter, so the higher frequencies from the gravel or some noise on the ground does not result in the motor being damaged. But there are problems. So the first problem is the design problem. We have to somehow insert a spring that will be able to carry the weight of the robot. So it has to be robust. It complicates the mechanical design of the servo motor. And it's basically trying to retrofit certain details in the older mechanism. It's fine, but it's an alternative to the outrunners that is not really commonly used. Here's Vitaly. So Vitaly can sign the papers. Hello. If someone has not signed the papers, Vitaly is here. Okay, so it complicates the design and also it complicates the control, because we have, imagine that you can push me by the shoulder and I will just start oscillating like this randomly without any control on that. So it will be not cool. We'll have to incorporate this extra degree of freedom, this passive part, not controllable part, into the dynamics. I will have to stop somehow. So if I'm oscillating, I will have to, I don't know, to hold certain object to stabilize myself. So these things are used not that often. They are used if they are very rigid. So if no oscillations occur because of that. And they're used in very specific cases when we cannot get without them. So if we cannot use outrunners, if we cannot use some springy elements like boots or something, I mean, for the robot, then we have to work on the servo motors like this. And this is Casey. Casey is a very nice robot. It was built pretty much following the idea of a leg of a bird, and it has a number of awesome properties. So let's talk about this robot for a bit. It does not open. So, to me, this is pure genius. It makes me cry during long winter nights. I'm kidding, but that's really cool. So, let's take a look at what is going on here. Here, the serial elastics is used, and this is one of, in my personal opinion, the best examples of what is it all about. This is a good case of using serial elastics. It's used only in one joint, so the robot is not becoming very too much under-actuated, so to say. We really introduce one element that we do not control, but this spring is it has a lot of the U module, or what it's rigid. What? Yes, it's rigid. So how does it work? This rod is rigid, and this spring over here, the spring is here. It's pretty stiff. So this whole
or even this whole 5-linkage system is used to bring the torque from both of the motors, these motors, to the knee. So the knee here is actuated through the link, and the genius part of the design is not only the spring itself that does the same thing as I did with an Achilles tendon. The second cool thing is that the motors are moved upward. The legs are very light, very lightweight, and this robot is robust to the ground conditions, to the surface condition. It was working. It was running blindfolded, by the way, no vision. It is capable of ascending the stairs blindfolded. So it's very robust in terms of the surface and conditions. And it's very energy efficient. It can run for 5 kilometers on one charge. That's outstanding. So a very cool robot, a very unique design. They've been working on it for maybe 10 years or something. And they followed the mathematical model. So first of all, this leg was more like a parallelogram, like this. So it just bounced, and there was the springiness, but it was symmetrical, and they tried out different control approaches. And after that, after the control started working properly, they thought to themselves, well, can't we just create a leg like this? It will be asymmetrical, and there will be a preferred direction of motion, but we'll keep this springiness, and we'll move all the motors. We'll keep all the motors upward. And then came Cassie, and the humanoid version Digit. It's just the same platform, but there's a part with the heads and the head on top. They're kind of expensive, but they're
Sorry, so if you don't have the serial elastics, what effect would it wouldn't? Could you explain what the effect would have been?
Yep. So imagine it does not have these elastics, and we are landing after the fly phase. If we're landing, our servo motors will experience a hit that will load the gear, the main gear, the gearbox, and it will reduce the time of its functioning, proper functioning. And another thing is we will have to dissipate the energy that is in the form of sound at this point in the material, so the energy is lost. The spring serves actually two purposes. The first is to mitigate the heating impact, and the second, it is conserving energy. We humans don't really conserve energy with the Achilles tendon like this, not very much, 30% I believe. But kangaroos, they do. They conserve a lot of energy with their springs, and that's why they can jump for crazy distances. So this is an exemplary case, one of the very cool cases of serial elastics. There is also parallel elastics, and that's another topic. And I'm personally very interested in this thing in terms of the research. I already have my topic of PhD for the PhD, but I would love to work with some students that will work with this. So what's the idea? Let's imagine that I am a robot and I'm going somewhere with a bag of heavy instruments. So what do? If we exclude the linear motion, let's consider the torques that are produced in the knee. They are always clockwise, or counterclockwise. I mean, they have the same sign, right? So wouldn't it be cool if we could somehow compensate for this torque, for the average of this torque over time? It would be cool. So the idea is to introduce a spring in the knee that will produce the average amount of torque that occurs during the motion. It is called gravity compensation in this case. If we will do the same for the shoulders. For the back of instruments, it will be not gravity compensation, but exactly the same idea. So what did the researchers do here? There was a dog, animal it's called, and they have introduced these elements, these parallel springs, that compensate for the, they compensate part of the gravity. And another cool thing, and the perspective topic of research, is to make the springs adaptive. Actually, we can change the stiffness and the zero position of springs with some tweaks, with some small servomotors that will rearrange the spring inside the arm, the leg. We can actually do that, but it's underdeveloped, still underdeveloped topic of research. It was not covered in its completeness. So I believe that at some point some of my students will work on this, but the topic is still vacant. So if you would like to, you're welcome. And the purpose of this is basically to save the energy. That's why. So less torque produced in the knee, less energy consumed by the motor. That's it. We can do that, sure, yes. There's no problem in adding any kind of springs to the system. We have tendons, so they are analogous to the springs. What we cannot do is we cannot use hydraulics. We cannot use pneumatics really. But pneumatics do not fit because it's more or less, it's much softer than we need really. And hydraulics are not allowed in RoboCup because they're unsafe. Because of the 300 bar, 400 bar, and if something breaks, everything will be covered for everything. And while I'm talking about this, it's not only connected to RoboCup, it's just the direction for researching.
You said the less torque produced by the knee is what you said more energy consumed. No, what did you just say? You said like the less torque produced by the knee.
Less torque produced by the knee,
Yeah.
less the energy consumption is.
Okay.
Yeah, the same as for the human. If I'm standing like this, I can stand for 5 minutes, and I cannot stand for 5 minutes like this
Yeah.
because of the energy consumption. And the torque is directly proportional to the current. So in this paper, people have spared 30% of the integral of the torque squared, or this is equivalent to 10% of the energy. And the cool thing is that they did it with a mechanical adaptation, with a mechanical device, because there's an overflow of papers with reinforcement learning fancy stuff, like we were training our neural network on 10 GPUs for 2 months, and now behold our 1.5% improvement. There's a ton of papers like this, and this paper is different. So people put some thought into it, and they have found out the optimal parameters of the spring. They made it mechanically, and it's a passive element. That's another thing. So the signals are cool, really. So they did it cool. They can really use less energy while doing exactly the same in terms of the locomotion and load capacity. About the adaptation, what I mean is, imagine that this dog is walking to one direction with a load of instruments and another direction without a load of instruments. So it would be cool if the parameters of the spring would be different on the way here and there. And we can really
calculate the optimal parameters given a number of the trajectories. So if we can observe the torques against the angles for 5 minutes straight for the knee, it will give us some insight about the compensation. So let's draw a plot of torque against the angle. Here's the angle in the knee, and here is the torque. So if I'm just moving like this, what will be the plot? Let this be 0 degrees, this will be 90 degrees. How the plot will look like? Linear? You sure? So there should be a cosine plot, right? Somewhere. Or sine. Sine it here. So it seems like something like this in the limited range. It doesn't look like a sine. Oh, no. Excuse me. Yeah. So it should be something like this, seems like. Yeah. So we can try to find a spring that will minimize the area under this curve. The energy consumption, or, well, yes, the energy consumption, where is it? Where is it? Okay, right here. It is the integral up to a certain coefficient of the torque square of T by dt. And we are trying to find a spring that will counteract the gravity forces. So imagine that we have introduced a new spring to my knee such that I can completely relax my legs and be stationary in this position. So what is this going to mean? It's going to mean that at a certain angle here, for example, I do not produce any torque. So the torque is 0. And if I'm going up, the torque has one sign. If I'm going down, the torque has other sign. The cool thing is that at first glance it seems like we didn't change much, right? We have just moved everything down. But the integral of the square will actually be smaller.
Also, what if the integral of the square is like that?
Okay, let's consider a separate example. The integral of the square of this function is greater than the integral of square of this function.
Yeah.
And here it's pretty much the same. The first case, this green function, is always positive. And
A negative number turns positive.
well, no, we're squaring, but the thing is that for the blue plot, more values are, so to say, closer to 0. And they introduce less impact into the integral of the square. That's why this could make sense.
Yeah, because it's
And the parameters of the spring could be found in the optimization process while we are trying to find such shift for the trajectory that will minimize the energy consumption. Okay, so that was a story about parallel elastics. Yes, this is the same robot. There are a couple of people
holding it during the test, and here the robot is descending the stairs blindfolded. Well, not blindfolded, but I mean without vision. Blindfolded means like it had eyes previously. It did not. So, domain randomization. What is that? The thing is, let's imagine that you would like to start to be proficient in juggling. Let's imagine that you have already juggled just balls, and then you can start juggling cubes, you can start juggling odd shapes, and then all of that will widen the range of different objects that you can handle as they move in. So you become more robust, more invariant to the specific circumstances of the environment. And here it's the same thing. So imagine we are training an object, or training an agent in the simulation. And of course, this agent will be very specific in picking strategies to work in this environment. However, we can start varying all the parameters like frictions, masses, delays, noises. We can randomize everything, and the only option that the agent will have is to find out a strategy that is robust to those changes. And this is exactly what the people did with Cassie. They have been training this robot in the simulation, but with all the different parameters, like the height of the step of the ladder, the length of the step, frictions, masses, all of that. And it happens so that they have really learned a controller that is capable of handling all the possible situations in reasonable situations that could happen. Not the mirror-shined, very flat surface here, but just some kind of concrete, maybe wet, maybe dirty, maybe dusty. But still, they have varied all those conditions, and the coolest thing is that it started working instantly. So they have replayed such an enormous number of combinations and options and variants in the simulation, so that the real environment lies very close to this range of options that they have considered during the training previously, which is cool. So imagine you have a server, a cluster, and it's producing some amount of heat, training, then you insert the controller into the robot, and boom, it's working. It's actually a rare case. It's usually not like this, but with a proper amount of domain randomization and tuning of the training process, it is attainable. Just say that it's one of the good practices in the field of reinforcement learning and training the robots to walk. If we do not want to program their walking by hand, which is actually the last resort. So if you can't make the robot walk properly with classical algorithm, with classical control, you have to get the reinforcement learning. During the last 5 years, I should say, the robots are becoming more democratical in terms of their prices. Our football robots are kind of expensive, but there are GitHub repositories and open builds that you can just download and reproduce in your garage. So you can print half of the details, and the other half you can buy in some internet shops that shop belts and gears and all of that stuff. So you don't need a 7 degree of freedom milling machine to produce this. It's being more and more attainable for normal universities or even schools. And there are some robots like this dog that cost unbelievably small amount of money.
Well, I mean, it's a lot, of course, but it's not as much as one could expect for such a robot that is capable of, you know, backflips and autonomous motion in the grass, and it's robust and fast, and there are cameras all over the place in it. So they have become much cheaper than you can think of on the first glance. What is going on in humanoids now? That's my personal opinion. What's happening is the dexterity, the agility is increasing. So the robots are slowly gaining the joints that were previously absent in them. If you take a look at the football robot, it doesn't have any joints that allow, you know, this motion of the torso. And well, these robots do not have the same agility as the human does, but at least they can incline. So they can move like this. They can also move like this. They can move like this. This robot is the it looks suspiciously close to a replica of the new Boston Dynamics Atlas. Maybe they did it independently, maybe they did not, I don't know. But the thing is that it's not Photoshop or something, it's just the footage. So this robot could really stand on one leg, and the other one is high in the ground. So their joint limits, I'm talking about the scale of maybe the last year, really. It's a very short span. The joint limits are becoming looser and looser, and that's cool. So the robots will be at some point capable of doing something like this. And another thing is, let's take a look at their feet. So here you can see the linkages that actuate the foot. So the motors are located higher above the ground, so that the moment of inertia is smaller. And this is one of the common practices. So people are regularly introducing linkages to the feet, and different motors start being more and more specific. What do I mean by that? Well, the yaw motor, this motor that rotates the leg vertically, is typically much less loaded than the pitch motor. So in this robot, in Fourier JR1, the pitch motors for the knee and for the hip are big, and the yaw motors are much smaller, and the roll motor is not that big as well. That's because during the regular walking, the most loaded motors are indeed the pitches of the hip and the knee. Well, yes, this is the knee pitch, really. It uses a linkage to actuate the lower part. So the legs are becoming more specific and adapted to the specific motions they perform, and they're becoming lighter, or it's better to say they have less moment of inertia. So we can compare these robots to the robots that we are going to work with. Our robots are good, but they are just not this kind of state of the art. So it's better to keep in mind their limitations. I'm saying all of this for the context. And in order to work with these machines, well, you have to be very much interested and join some university that does this kind of research. But universities do research, so it's possible. Yeah, I think I have said about, yes. How far are the robots from the humans? Very far still. So there are certain things that the humans cannot do, like we cannot substitute
an excavator. The excavator will be more powerful. However, we are very versatile in terms of what we can do. We can do pull-ups, and with the same hands we can perform very small motions, like ironing S&D components somewhere, and between one activity and another, we can have like 10 seconds. So we have enormous dynamical range of the amplitude of our motions and the power of our motions. We have tactile feedback in the orders of thousands of sensors. That's why we can manipulate objects in the ways that are not attainable by the robots currently. And some of the modern papers about tactile feedback, they include arrays of sensors like 10 by 10. That's pathetic compared to living organisms. So there are certain areas that indicate that the engineers, control engineers, roboticists, they will have things to do until we'll become old and we'll start, I don't know, growing crops on the dash. So we'll for sure have things to do. People from time to time ask me, what do you think? Will it all be over or not? I mean, will the robotics will be closed? So are we done? Can we just go do something else? Aren't all the problems solved? And usually I respond that no, not yet. Not all of them are solved. We have the difficult emotions that the robots are not capable of performing. And also they're still stupid. Because, well, yes, they are. I can manipulate objects in my pocket, and I will remember after that the order in which they were lying there. And it's not attainable by a robot. One more thing. Infinite dimensional objects like liquids, membranes, or even cloth. It's very difficult to fold it. Very difficult. We use two types of feedback. I'm using two types of feedback: the tactile feedback and the visual feedback. And to make robot fold cloth properly, whoa, just try imagining a manipulator to create a bird from, like origami bird, you know, those ones. This. Try programming frame by frame a manipulator to create this. It will be just a nightmare, right? And folding cloth is more difficult because cloth is deformable and it behaves in a strange manner. So it can have multiple layers. It could stretch differently in different directions. And the robots are not even close. So the robots are not even close to sewing, for example, a pair of pants. That's another goal. It will, I don't know, we can talk in 20 years about that. It's so far away from now. In terms of the locomotion, well, yeah, there are cool things. This is not a video, okay. Probably you've seen that. So the robot is doing backflips, and it's really, yes. The robot is doing backflips, and it's very cool. So a trained human could easily do all of this, right? And there are things that humans can do that robots cannot. For example, from the same field of extreme sports or acrobatics or something, imagine BMX, like the backflips in the air on a bicycle. They do crazy stuff like 4 rotations, 3 rotations, and it involves whole body manipulation and control during the flight phase, which is still not possible. You know, cats, they tend to rotate completely during the flight so that they land properly with their feet down. So the humans are really capable of doing the same stuff, and robots are not yet, because they don't have all the proper excessive degrees of freedom. By excessive, I mean the torso joints, all the shoulders, all of this. They don't have this, so they cannot explore the complex non-linear dynamics of what cats and humans can do during the flight phase. Flight phase is difficult because we cannot exert any forces on the surrounding. We have to somehow rearrange the position of the body so that we are oriented properly and we can land safely. So robots cannot really do this at this point. By the way, a question. How do the cats do that? Do you have an idea? So, do they spin clockwise as the tail rotates counterclockwise, or what? What do you think?
They have a sense of gravity at all.
Yes, they do. They have a sense of it. How do they actuate themselves so that they rotate? Imagine if this is a cat and it's oriented wrongly, it cannot interact with anything, but somehow it rotates and flips. How do they do it? The arms. Well, yes, they use their arms, but how do they? Where do they get momentum? That's a good guess, but cats with small tails do it as well. So no. Tail is involved, but tail is involved only because it's a part of the body of the whole cat, so it is used to using the tail. It can do it without the tail. Yes, but how? Imagine a brick is just falling. It's not rotating, right? It will just fall as it did, and the cat is somehow flipping. How does this happen? It's a question about control, by the way.
Their center of mass they rotate them, they don't want to have
You're close. So imagine the following. Yeah, the first thing, the angular momentum is conserved. This is one of the laws of nature. But angular position is not conserved. That's the thing. That's why they can rotate. The position is not conserved. You can move infinitely slowly and get to some another position. So imagine this is a cat, two-linkage cat, and it's oriented incorrectly. Well, it's a theoretical cat for sure. So what we can do is we can fold the cat like this, then we can rotate. We can do it, right? And then we can unrotate it back so that the final position will change. Okay, it was not clear. Let me find something. So these are the legs of the cat, okay? And they're facing upward. The cat is falling. It is folding, then it's doing a motion like this, and then it's unfolding. And it has changed its angular position without taking any angular momentum from anywhere, because it cannot break the laws of nature. But it could attain any position with this. Again, like this. Here we can rotate, and here we are in a different position again. Sorry, I misdemonstrated, but you get the point. So this is the simplification, and of course they use their whole body dynamics, and we cannot express completely the whole complexity and the grace of the cat's movement but generally speaking, it's something like this. So they exploit that the angular position is not conserved, so so that they could rotate and land properly. And it's very difficult. The robots cannot do that yet. One of the recent papers that I've seen about that is that the robotic dog is jumping from the shelf or something, and it's doing 360 or even half of the backflip. So it's still in the infant phase. Well, yes, I've talked about that already, and the last is it's not about the robotics. It's about the roboticists and the field. So it's difficult to start doing robotics. It is not always clear what are you going to do if you become a roboticist. It depends on the country, but this is a pretty common problem. And there is a very huge gap between what is usually perceived as robotics by, say, parents, which means Lego, Arduino, that kind of thing, so a very small, easy controllers, and the real practice, like these KUKA hands that pick and place stuff. So that was the intro. Thank you. Let's get back to this class at 1 p.m.
And physics was too much.
Yeah. Is this recording?
Yes.
Yes, it is.
Oh my god, it's so me. That was so